All right, heading into 3.2 then. Here we're talking about reciprocal of a quadratic function. So yesterday was a reciprocal of a linear function, which basically means you had something, a binomial with x to the power of 1 in the denominator here. And today we're going to have things with 1 or any other number over a quadratic. So something in the form ax squared plus bx plus c. Of course, that could take other forms. It could be in factored form, where the product has a term of x squared. And we're going to see what that does to the graph. Here we go. Below is a graph. So on your opening page, we have a little bit of an investigation here. Below is the graph of f of x equals 1 over x squared. That would be the most basic reciprocal of a quadratic function. And we're going to find out some things. What's the horizontal asymptote? The line that the curve approaches but never touches, horizontal.
Well, in this case, it'd probably be 0.
Yeah, let's put that in the form of an equation of a line.
Y equals 0.
Y equals 0.
For vertical would probably be x equals 0.
Vertical asymptote at x equals 0. Intercepts. X intercepts?
Nope.
Y intercepts?
Nope.
None. Domain and range. X belongs to a set of real numbers. What's the restriction?
It's not equal to 0.
X can't be 0, right? If there's an asymptote there, then the curve will never touch that. The function will never touch that. And the range?
Y is a set of real numbers, and then y is greater than 0.
Thank you. Y is greater than 0, not greater than or equal to, just greater than 0. We can see that the whole function is above the x-axis there. Step 5, end behavior. So end behavior means as x approaches negative infinity and as x approaches positive infinity, we want to find out what's happening to f of x. Where is f of x going? Who can describe that?
Y approaches 0.
So in both cases, yeah, we're going to go f of x approaches 0. It's getting closer and closer to 0. We'll never touch it though. Yep, either way, y f of x. Positive and negative intervals. So this is where is the function itself positive and where is the function itself negative.
It's always positive.
It's always positive. So now we need to be careful. We can't say it's positive, x belonging to the set of real numbers. That would be false, okay? Because we have a restriction where we know it can't be 0. So where is it positive? We could say the whole domain. The whole domain. If you wanted to do this another way, you could say x less than 0 and x greater than 0. Okay, that doesn't tell us what happens at 0, but we don't need to know that. We just need to know where it's positive, and it's positive over these two regions. And again, you could use bracket notation for that as well. Is it negative anywhere? No, it's never negative, the function. And now that was the value of the function, positive or negative, but now we're looking at increasing and decreasing intervals. So where is this function increasing? Where is it increasing?
When x is less than 0.
Good. And where is it decreasing anywhere?
It's decreasing when x is greater than 0.
Over that whole region, it's going to be decreasing. It will never get to 0, and it'll never reach the negatives, but it is still decreasing. It's decreasing by less and less and less each time. All right, your second graph there that we're going to talk about, similar questions, is the graph of g of x. You can see it's a little more complicated. The quadratic in the denominator is x squared minus 2x minus 15, so there's a bit more going on here. And we have a numerator of negative 10. and we are asked, 1, to determine the restrictions on x and then state the domain. So how are we going to determine the restrictions? Basically, determining the restrictions means what is x not allowed to be. And if we have x in the denominator, well, we're not allowed to have the denominator equal 0. So in order to figure out what x actually can't be, what do we need to do to that denominator of x squared minus 2x minus 15?
Well, x squared subtract 2x can't equal 15.
Good. Okay, so the restrictions then would be that. Sure, we could write it that way. Now, how are you going to actually figure out the values of x that it can't be? How would you solve a quadratic? Right. Solve by factoring. Okay. So I'm looking for two numbers that multiply to negative 15, add to negative 2. That's going to be x minus 5x plus 3. From that, we get two values that x can't be. X can't be positive 5, and x can't be negative 3. Okay, there's our restrictions. Once we have our restrictions, we can finish the second part of this, which was to state the domain. So x belongs to the set of real numbers. I can put any real number in there except I can't put negative 3 and I can't put 5. And maybe I'd put... Okay, we try to put those in chronological order. So you start with the lowest number and then the higher number. Good. In step 2, describe the behavior of the graph to the left and right of each asymptote. Okay, so here we're connecting to our restrictions. If x can't be negative 3, then we must have an asymptote at x equals negative 3, and we have an asymptote at x equals 5. And we'll get into more exact language, but we want to look at what's happening. Well, we'll do it right away. So as x approaches negative 3 from the left, what's happening? So we're reading from left to right, and we're getting closer to negative 3. Where does the value of the function go?
Where's the asymptote again?
So it's at negative 3. So your graph looks a bit like...
Oh, okay, I see them now. Never mind.
You have an asymptote here at x equals negative 3. You have an asymptote here at x equals 5. And we're reading from left to right. And as we approach this asymptote, what is the function doing? Zoom. Heading all the way down to negative infinity. Well, what about as x approaches negative 3 from the right? Now we're reading from right to left. What is the value of the function doing?
It increases.
Yeah, it's going into super positive land. Positive infinity. Okay, same thing for the asymptote at x equals 5. As x approaches 5 from the left, so we're reading from left to right and we're coming toward the 5. What is the value of the function doing?
Approaches infinity.
Also going to positive infinity. And as x approaches positive 5 from the right, so we're reading a little bit backwards, right to left. This thing's heading down to negative infinity. All right, there's our our behavior to the left and right of each asymptote. So this picture is a little more complicated. So it warrants an investigation into the slope and the change in slope for the different intervals. So we're going to use the terms that we discussed yesterday as far as negative and increasing, or negative and decreasing, or positive and increasing, positive, decreasing. We're going to talk about each branch. So to the left of the leftmost vertical asymptote. So here's what we're talking about right here. Okay? We're reading from left to right. What is happening to the slope? Is the slope positive or negative in this region? It is negative. 3a negative. And is it increasing or decreasing? Is it getting closer to 0, or is it getting more and more negative?
It's getting more and more negative.
More and more negative. So it is decreasing. So we have negative and decreasing. It's going further and further into negative land. Okay, what about to the far right? To the right of the rightmost asymptote. What kind of slope do we have?
Negative and increasing.
We're reading left to right. Now again, sorry, slope we always...
Positive and
Okay, so it's positive because it's going up. Positive.
decreasing.
And it is decreasing. Okay, it's never going to get all the way down to 0 or a negative slope. It's never going to come back down, but it is decreasing. It starts out very, very, very steep, and by the end it's almost 0. So it's net positive, but it is decreasing, and that is going to last infinitely. Okay, well, those two branches were pretty easy. What do you notice about this whole U-shaped thing in the middle, if we're reading from left to right? How would you describe that slope?
As it, from the left of -1, it is positive and decreasing.
It's the slope.
Slope. Yeah. No. It's negative and increasing.
Thank you. So this little portion right here, it's negative and increasing. But then what happens?
After, and then from 1 to -5, I guess, it's still positive, and no, it's positive and still increasing.
Okay, so it's increasing, and at this point it hits a little apex or a minimum point here, and it is actually going to cross over through a slope of 0 into being a positive slope. Okay, we haven't dealt with that before, but you've got negative and increasing, and then it's increasing, increasing, increasing. It doesn't hit a limit. It keeps on increasing until it goes back into positive land, and it creates symmetry on either side of this middle point. Now, if we're going to be describing these things, or we're going to be identifying intervals of positive slope, negative slope, increasing slope, decreasing slope, what do we need? We need to be able to find this point. How would you do that?
Sorry, I missed it.
So if we want to be able to talk about the slope on the pink side and the slope on the blue side, we need to know what this point is, because that's where the change happens. That's where our interval is going to be separated. How can we find that point to help us actually talk about these two regions?
Is it halfway between the two?
It's exactly halfway between the two asymptotes. Keep going. That's how we're going to find it out.
Can we get a tangent to touch it at one spot?
What's the point called that's in the middle of something?
Oh, the vertex. Kind of.
Okay.
Not really.
If you needed the middle of two numbers, what would you do?
The average? Maybe.
Find the average.
Oh.
And we're just dealing with
Oh,
x values in the asymptote. So find the average of the x values. I'm probably not writing this in the most succinct way, but find the average of the x values of the asymptotes. And we want a point. We want x, y. So now what do I do once I find the middle x? Then we're going to sub into our function. Sub into our function to find the y coordinate. Okay? So that's what we're going to be working on. We need to find this point in order to discuss these two intervals as well. So we're going to find that x coordinate. That's easy because it's right in between x equals -3 and x equals +5. So we know that's x equals 1. And then in order to find the corresponding y coordinate, we're going to throw 1 into our original function, do the math on it, and get that y coordinate. And then we can even talk, and you might not even need the y coordinate always. You might just need to talk about, x from -3 to 1. And then what happens at 1, you have a slope of 0. And then from 1 to 5, what do you have? You have positive and increasing. Okay? Good. The last question there, number 5, simply says, briefly explain how these graphs are different. I'll do that quickly. The first graph has 2 legs, and they're both going the same direction. The bottom graph has 3 little sections. The 2 on the outside actually look just like the original situation, except in this case it's they're negative, they're going down. And then they're kind of split up, they're kind of separated by this U-shaped thing coming in there. And this U can be tighter or wider depending on where the asymptotes are, which depends on the factors of the expression in the denominator. State the domain. What do we need to do?
Well, find where x, or no, find where the denominator is equal to 0.
Good, so we're going to factor the denominator,
Yeah.
and then we're going to solve. Okay, well, the denominator here is a difference of squares.
X equals to x subtract 2.
So it's x plus 2, x minus 2, the product of a sum and a difference, which gives our restrictions. And the restrictions are?
X is not equal to -2. X isn't equal to +2.
Good, which gives us our domain. X belongs to the set of real numbers such that x cannot equal -2, x cannot equal +2. Now we're looking at the equation of each asymptote. That's fairly straightforward. If there's a restriction on the curve, on the function, then that's where an asymptote is. So x equals -2 is an asymptote, and x equals 2 is an asymptote. Describe the behavior of the function near each asymptote. Now, I'm going to help out with this one a bit, but basically what we're doing, and you guys have a graph there. You can add your asymptotes already. So you can give yourself a dotted vertical line at -2 and at +2. It just gives us something to talk about. X equals -2, x equals 2. And we want to look at what is happening as x approaches. So now you can see with 2 asymptotes, we've split this function, the graph of it is split into 3 separate parts. Okay? The 2 on the outside are either going to look like this and this, or like this and this. And the U in the middle is going to do the opposite. So if our outsides are in the bottom, the U is going to be up here doing this. And if the outsides are in the top, the U is going to be upside down doing this. Okay? So we need to figure out what's happening at these asymptotes, and that'll give us a really good ability to draw this thing. All right, so as x approaches -2 from the left, and as x approaches -2 from the right, we want to figure out what's happening. You can do this. We've done this before using the number chart, doing a chart, and that's helpful. So, but let's just consider mentally a couple of numbers. So we're going to read it from left to right. So we're to the left of -2. Let's take -4. Okay. If I put -4 in here, I get -2 times negative 6, which is 2 over 12, which is 1/6. It's positive, okay? It's positive and it's 1/6. So I'm just going to leave that out so far. I'm just doing some things in our head. Let's see what happens. So we're at positive 1/6. Now if we put in, let's say negative 3, what happens? Well, we end up with negative 1. We end up with negative 5. That's positive 5. That's 2/5. So now all of a sudden we're at positive 2/5. Well, that number is growing and it's positive. I could get closer and closer. I could take negative 2.5, negative 2.1, okay? But what's happening here is we're positive and we're growing as we move from left to right. So it's going to end up looking like this. Yeah? It's going to come up and do one of those. Now to confirm, we'll look at what is happening as we approach this thing. Well, I should write down what we actually did. We found out that f of x, as we approach negative 2 from the left, f of x is approaching infinity. As we approach from the right, so we could take a value like 0, because that's right in between, and then we could take negative 1, and that's getting closer to our asymptote of negative 2. So let's take 0, we'll put it in here. We get positive 2 times negative 2 in the denominator. That's negative 4. We've got 2 over negative 4. That's negative 1/2. So we're negative. That's good to know. And let's take negative 1. We'll put negative 1 in here. Negative 1, we end up with positive 1 in the first bracket, negative 3 in the second bracket. So we end up with negative 2/3. Negative 2/3. So 2/3 is bigger than 1/2. So we're going down, 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 down as we're looking at this thing. It's going to look something like that. Okay. And I can draw this, stretch this out a little bit for us. And for this, we're not going to do the rest of it. Okay, it's the rest of drawing it out. Basically what you would learn is you would do as x approaches positive 2 from the left, then x approaches positive 2 from the right, and you would learn that it's doing something like this and something like this. Okay, you get pretty familiar with that after you do it a bunch of times. And so we've graphed it. X and y intercepts. It does not have an x-intercept. There's nothing that I could put in for x to make this whole thing equal 0. Okay, so there is no x-intercept. But for the y-intercept, I do want to find the y-intercept. The y-intercept occurs where x equals 0. So for the y-int, I just have to put 0 in for x. I end up with 2 over negative 4, or negative 1/2. So that's really helpful too. It tells us that our y-intercept right here, which we've already kind of drawn, is negative 1/2. That is a key characteristic of this graph. You would have to find that out if you had to find out all the key characteristics. We should note that there are no x-intercepts, x-ints, none. We've sketched it already, and once we've sketched it, it becomes pretty easy to state the range. Here we have the range as y belongs to the set of real numbers. Y cannot be 0. And it's really all there is to it. Finding the key characteristics. This we didn't have to do a whole lot of work factoring it because it was a difference of squares, but the restrictions come right from the denominator. Okay? The restrictions correspond to the asymptotes. Where the function can't be, that's where the asymptotes are. Then finding end behavior is something we've done in previous lessons. You could, if you want to make note of how you could do this more effectively, you'd basically set up a table of values. And as x approaches negative 2 from the left, you might look at negative 3, you might look at negative 2.5, you might look at negative 2.1, and then you'd get a pretty good idea. You'd sub those in to the function, you get a pretty good idea of where the function is heading. Okay, you would have to do that for x approaches -2 from the right. You'd also have to do it for x approaches +2 from the left and +2 from the right. So you're looking at 4 little tables like this each time. But again, once you have enough information, you can stop and write down what's actually happening. So we should have at least written what's happening at all of these places. So maybe we'll do that quickly. As we approach -2 from the right, we're heading down to -infinity. And then I can do the same thing for my other two guys. As x approaches +2 from the left, f of x is heading down to -infinity. And as x approaches +2 from the right, reading backwards, x is heading to positive and y is heading to +infinity. Because you should record that information even if you didn't do all the work to figure it out. Then you can graph it, get the y-intercept and the range. Good. In example 3, our focus is on the rate of change. So our focus is on the slope in different intervals of the graph. Okay, so we're given a function. We've got f of x equals 1 over 2x squared minus x minus 6. So the first thing that we want to do in order to talk about this is always going to be factor the denominator. Okay. Basically, the first thing you're going to do almost all the time is factor the denominator. We're not going to show how to do it, but you would need to use factor by grouping, okay? And we end up with a denominator of 2x plus 3 times x minus 2, which gives us our restrictions. X can't equal -3 over 2, which is -1.5, and x can't equal +2. That corresponds with our asymptotes as well, but all we really want to know is that that gives us our intervals to talk about. So we are going to end up with 3 intervals to talk about. Intervals to consider are 1. We've got from x is less than -3/2. So if you were thinking about this on a number line, basically you have an asymptote at -3/2 and an asymptote at 2, and here are your intervals that you're talking about: 1, 2, 3. So the second interval is in between the two asymptotes. It's from -3/2. X is greater than that, but x is less than 2. And the third interval, I'll just write it over here. I'll write it here. 1, 2, 3. The third interval is x greater than 2. Okay, so in each interval, we need to know what's happening at to the slope within each interval. So in order to talk about slope, let's just say hypothetically that this on this side it looks like this. Okay, it doesn't. I have no idea what it looks like yet, but we want to talk about the slope maybe in this area and then the slope in this area. But how do we talk about the slope? We need 2 points and 2 values of the function so that we can use our rise over run formula. Same thing here. We're going to do that for each of the sections, but we're actually going to have to do 4 sections, because what happens in this middle section? What happens in the middle interval? It's either a u going up or it's a u going down. So the slope isn't consistent. Slope is going to be positive and change to negative, or it's going to be negative and change to positive right in the middle of this interval. So we're going to need to find out where the middle of that interval is as well. Okay, so these are fairly tedious questions. They take a while, but if you work carefully, you can't really mess it up so badly. Okay, so let's look first at our first interval to the left of negative 1.5. And we'll take a couple of points. Again, we always want to organize our thoughts left to right. So we're going to look a few digits to the left here. We're going to start with what's happening at x equals -4.
Sorry, I missed it. What's the branch? Is that just in, like in the first questions, describe the increasing and decreasing intervals in the branches of the function?
So that would be kind of this, yes, the 3 branches or the 3 intervals that are worth talking about. So now we're going to discuss the slope within each of these intervals.
Okay.
So in the first interval, we can take the test point well to the left, and we can approximate the slope at that point by considering x equals -4. Okay, so basically if I draw this out again on a number line, you've got your asymptotes at -1.5 and at 2. We're looking at what's happening in this region. We're going to start way over here at -4. Look at what's happening there. Then we're going to look at what's happening at -2. We'll compare the two slopes, and then we'll be able to find out if it's doing this or if it's doing that. Okay? So x equals -4. What's the value of the function at -4? You would punch it into your calculator. I'm just going to tell us it's approximately -0.03333 ongoing. And in order to find the slope of a secant around that point, we can also then choose x equals -3.9. So this is how we approximated instantaneous rate of change. This is the slope of the secant, which is the average rate of change over a small interval. The value of the function at -3.9 is approximately -0.0198. So then, to get the slope, we need the change of y over the change in x. So the slope at this point, we can call it slope 1. So we're going to end up doing this several times. Slope 1 is the change in y over the change in x. I'm going to write it in this form, and then I'm just going to give the answer. So we've basically got f of -3.9 minus f of -4. Okay, that's the difference in the value in the function over this interval. And then the difference in x is -3.9 minus -4. And I made a typing error. This value is not right. I got that from the wrong place. Okay, the value of the function at -3.9 is -0.03352. So the slope here is approximately -0.02. All right, that's one location to the left of our leftmost asymptote, and we've got the slope, very slight slope, but negative. So now within that interval, still, we're going to test the slope at x equals -2. X equals -2. We need to find out what f of x equals at that point. It equals -0.25. And we need another point really nearby in order to create a secant line and get the average rate of change. Let's pick -2.1. The value of the function there is -0.20325. And then if we get the slope of that by going rise over run, or y2 minus y1 over x2 minus x1, we end up with a slope of 0.56, -0.56. All right, what did we learn? So is the slope positive or negative?
It's negative.
Slope is negative. And is it increasing, getting closer to 0, or is it decreasing? getting a bigger negative number. So we go from almost 0 down to more than a half negative.
So it's decreasing.
So it's decreasing. Okay, so we just found out that in this leg, in this range, in this area, we're looking like that. Okay. Now, we're going to assume knowledge that gives us this. Okay, in this last interval, what is happening? We're just going to say what's happening. The slope is positive and decreasing. Okay, so here we have, therefore, slope is positive and decreasing. Okay, that's review from last lesson, but what I want to talk about is this this other interval, because that's new to us. This middle interval, interval number 2. Okay, we know that there's going to be either a maximum point or a minimum point in that interval. Our goal is to find that point, or at least the x-coordinate of that point. Okay, so first we want to find, if you're organizing this on your paper, you might be able to do a better job than I'm doing, but basically you're going to take this second interval, this middle interval, and the first thing we're going to do is find the halfway. Basically find the middle of your asymptotes. So we've got negative 3/2. The x-coordinate that we're looking for is negative 1.5 plus 2 divided by 2. That equals, in the numerator, you're going to have positive 1/2 divided by 2. Okay, positive 1/2. If you have half and you split it in half, you end up with a quarter, right? So you're looking at 1/4 or 0.25. Okay, that's the x-coordinate that ends up right in the middle. So this is the next division that you were talking about. X equals 0.25, positive. So now what we need to do is we need to consider what's happening just to the left of that and just to the right of that in order to figure out what the slope is like, in order to discuss what the slope is like in those areas. Good. So the next step then would be to find the value of the function at that point. So the value of the function at that point, we just sub in 0.25 into our function, and it pops out 8/49, which we can translate into a decimal as 0.16327. We don't want to round too early in a lot of these. You notice we're keeping 5 decimal places. We don't want to round too early, because then, you know, these two numbers would look exactly the same. And that happens in other places too. These two numbers would be, they would go different directions, but they'd be super different if you rounded. This one would go all the way to negative 0.3, and this one would go down to negative 0.2 if you rounded to 1 decimal place. Anyway, consider points just to the left. So to the left of this middle point of x equals 0.25. We could use our coordinates there even. It's 0.25, comma, 0.16327. What information do we have already? We know the sign of our y-coordinate, which means this thing is positive. So we already know what it's going to look like, but yeah, testing our slope. And then to the right, basically let's just draw it. You would test 2 points just like we did over here. You'd test 2 points to the left of this point and see what's happening as it moves away from that middle point, and then what's happening as it moves to the right of that middle point. And we'd end up with something like this. and we'd be able to talk about those intervals. This interval now is going to get split into two, right? So now we have from negative 1.5 to 0.25. So I'm just going to go do, as in fill in the blanks. And then for the interval where x is greater than negative 1.5 but less than 0.25. Somebody describe that slope in this region.
That's going to be negative
It's negative
and increasing.
and increasing. Negative and increasing. For 0.25 to 2, what's happening to the slope?
It's positive and still increasing.
Positive and increasing.
Yeah.
Thanks very much. Another way we can think about this is we can put it in a table. So, do you guys have a table there? No. You could summarize that information in a table. Doesn't matter. We've described it fair enough. We've got all the sections. This section over here, we know that we are positive and decreasing. In the middle, we have a split into two intervals. You need to know how to find those two intervals. The split point is just the middle of the asymptotes. In example 3, describe key features of a function. This one ends up being a bit funny. So it's the same question, right? Describe key features of the function, but this function itself ends up having a funny kind of key feature. So here we go. We are given f of x equals 1 over x squared plus 4. For the domain and vertical asymptotes, we would usually factor the denominator, okay? But this is not factorable. But we're trying to find, so for restrictions, we're looking for x squared plus 4 equals 0. Can you think of any values of x that can make that thing 0? Well, if I put a positive number in there, I'll always get a positive plus a positive, which is always going to be greater than 0. If I put a negative in there, a negative squared is just a positive. So there are no values that can make this 0 or less than 0, okay? Since x squared is always greater than or equal to 0, x squared plus 4 is greater than 0 for all values of x. Therefore, no restrictions on the domain. No restrictions on the domain. And no vertical asymptote. All right, so what is our domain? Well, if there's no restriction on the domain, it's just x belongs to the set of real numbers. Okay, we can still find our x-intercept though. For your x-intercept, you set, you let f of x equal 0. Are we going to find an x-intercept? Is there anything that makes the whole thing equal 0? As long as there's no x in the numerator, you're always going to get no x int. Okay? The horizontal asymptote is always going to be x equals 0. but we can find our y-intercept. That's what happens when we put 0 in for x. We end up with a y-intercept at 1/4 or 0.25. And from there, we can draw it, okay? It's kind of an awkward drawing. Do you have a graph there on yours? An empty graph? So this thing is always positive, tells us that. It's always positive. If we tested some values, we could do some, we would want to find out what is happening at our end behavior. Okay, so let's look at what happens. Maybe I should write that, skipped a part. End behavior. End behavior as x approaches negative infinity. So as we move to the left, what's going to happen to this thing? Well, it's going to get smaller and smaller and smaller and smaller because the bigger x gets, well, even though it's negative, because a negative squared is a positive. So as x gets further and further negative, the denominator is going to get bigger and bigger and bigger and bigger and bigger and bigger and bigger. Well, as the denominator gets bigger and bigger and bigger, what's happening to 1 over the denominator? It's getting smaller and smaller and smaller and smaller. So now you have one part, but the parts are getting smaller and smaller and smaller and smaller and smaller and smaller, okay? So this thing is heading, as x approaches negative infinity, f of x is heading to 0. And as x approaches positive infinity, same thing's going to happen. We're going to approach 0. Because again, as the denominator gets bigger, the function itself gets smaller. It's a reciprocal function. But we do know we're in positive land all the time. So here we go, it's heading this way. Right, right. And typically, don't draw this, but typically we'd look like that. Right? But there's no restriction on the domain. So this vertical asymptote never happens. Instead, we have a y-intercept at 0.25. So look what ends up happening is you get a little bump.
Oh. That's interesting.
So you have a point at 0.25. And this is the graph of f of x equals 1 over x squared plus 4. Okay, so this one was special because there were no restrictions on the domain. There were no values of x that would make the denominator equal 0. So there is no vertical asymptote. But the end behavior still kind of behaved the same. We had to be careful about where we were because we're now working in the denominator with the variable, which is a little bit harder to understand. But then we found out that it doesn't actually go to positive infinity anywhere. Instead, it hits this 0.25 and comes back down. From there, we can get our range. The range then is y belongs to a set of real numbers. The range is pretty restricted, though. It is always greater than 0. But it is less than or equal to 0.25. Okay, it's stuck in this little channel. It never touches 0. That's why it is greater than 0, but it does touch 0.25. That's why it's less than or equal to.
Do you mention for end behavior that it approaches 0 from above? Or do you only mention that if it approaches from above and below at different points?
That's a good question. You could do that. Yeah. Yes, that is important. So in this example, it's noted, sorry I didn't write it, but it's noted like this. And f of x is positive. F of x is positive. It's the same as saying from above, from above. Yeah, good question. Either way works.